atomic age was born. There is no denying that since that moment, the shadow of the atom bomb has been across all our lives. All men of goodwill earnestly hope that a realistic control of atomic weapons can and will be achieved. In the atom, a particle so infinitely small that it takes over 100 billion atoms to make up the head of a pin. Just as other millions and quadrillions of atoms are the tiny building blocks which make up everything in the world. Ships, and shoes, and sealing wax, and cabbages and kings. Although no one has ever seen an atom, scientists have learned a great deal about how they behave, and there are widely accepted theories as to what they're like. This followed as scientists devised ever more powerful particle accelerators, commonly called atom smashers, to transmute more and more kinds of atoms. All scientifically important, but hardly world-shaking. Then, in 1939, some scientists were experimenting with transmutation of uranium. What would happen, they wondered, if they fired a neutron at a uranium nucleus, already the heaviest in nature? Why not try? So they tried. And the result? Nuclear fission. Instead of a minor change, the atom split in two. Truly a discovery to change the world. For what had happened when the uranium atom split was a kind of double miracle of science. Half of the miracle concerned that binding force we spoke of before, that kind of cosmic glue which holds the atom's nucleus together. We still don't know all about that binding force yet, but we do know it is equivalent to mass. Therefore, we may speak of it as having a kind of weight of its own. Now, the two atoms into which a uranium atom splits also have binding force. But for some reason, it takes less of that glue to hold them together, and in the process of fission, a tiny fraction is left over. What happens to it? It explodes as energy, proving Einstein's theory that mass and energy are really the same. But we spoke of a double miracle. To understand the second one, let's slow down that fission 1 million or so times. A single particle starts the reaction, splitting the uranium atom. Here now is the release of energy as heat and blast. Here are powerful rays being given off, similar to X-rays. But here are free neutrons driven out with tremendous speed. And provided there is sufficient U-235 present, what science calls a critical mass, those neutrons bombard other uranium atoms, causing them to split and split still others. The result? A chain reaction. Over 1 million billion atoms exploding within 2 seconds. The chain reaction process in the reactor creates tremendous heat, which scientists have learned how to control. Thus, a reactor may be substituted in many industrial applications where heat is now provided by coal or petroleum. But such uses in the foreseeable future are limited. For one thing, a reactor pile must be shielded to protect the workers around it from dangerous radiation, and this shielding adds tremendous weight. However, an atomic energy power plant has already proved feasible. The future supplying of electric power to entire cities is far from impossible.